So in the last class, we have discussed what is a covering space, what is a covering projection, what is a base space, what is an evenly covered neighborhood of some point in a base space. Uh, and we have discussed some examples also. So today we'll see few more examples and then some results. So this is example 5. Uh, for in integer n, uh, the map P from S1 to S1 the map P from S1 to S1 defined by P of Z equal to Z to the power n. This is a covering projection. Covering projection. So if the particular case we can see here so if you take this n equal to 2, copy of S1 and then another copy of S1, then what happens that this semicircle, right, this completes one round and then this another second portion of this completes another round, right? So when you complete one round here, you are completing two rounds here, right? So if you take any point here, right, take any point here, and then uh, an open set, if you take just an open arc here, then its inverse image, you can see that it is going to be an open set very small here, and then again an open set which is very small here. These open, any two open arcs circle, they will be homeomorphic. Obviously this will be uh, in fact if you restrict your map over this, then that itself will give you homeomorphism. Next example we can take for any integer n, the map P from Sn to Pn which identifies the antipodal points. antipodal is a covering projection. Right. So if we just consider the case for n equal to 2, right? Just for illustration, then so you know that this will be projective uh, plane if you identify the antipodal points of this boundary circle. This hemisphere, if you identify the antipodal points, right, of this uh, circle, right, then you will get a and this you can obtain of course by identifying antipodal points of this sphere. So if you just take an open set here, right, if you take an open set here, then you'll get its inverse image will be an open set here, and an open set here. And these two, this will be homeomorphically mapped to this, and this will be homeomorphically mapped to this. So similarly, you can see for higher dimensional cases for n greater than 2. Next, 6, if G is a topological group, topological topological group, and H is a discrete subgroup of G, discrete subgroup of G, and this is the space of left, right, cosets. Then the projection, then the projection P from G to H is a covering projection. So in order to verify this, it requires some results from topological groups, related to topological groups. So we're not going to verify this. Well, just if you know this about topological groups and some results related to them, then you can try this. Next. So of course here we are considering the projection map, right? So the covering projection, they are considering to be surjective. Right? So from our definition, it should be clear. So a continuous map a continuous map f y to x is called a local homeomorphism if each y belonging to capital Y has an open neighborhood which is mapped which is mapped homeomorphically onto an open subset of so just see that suppose you have y some x and there is a map f, right? So f is called a local homeomorphism if for every point y, small y in capital Y, there is an open set, right, containing Y, that will be an open neighborhood also of Y, which is mapped homeomorphically, right, onto an open set subset in X, right? So this is U, then this is U. Now, suppose we have a local homomorphism, then we are going to observe that it is an open map. So lemma a local homeomorphism, a local homeomorphism is an Proof is very simple, right? Proof is very simple. If you take what you have to prove, suppose f from y to x is a local homeomorphism. We want to prove that it is open map. So if we take an open set V, if we take an open set V in Y, we want to prove that f of V is open in X. So because V is open and F is a local homeomorphism, so suppose your V is here, right? Every point inside V, there is an open if you choose any point in V, then because F is a local homeomorphism, there is a suppose we choose here uh, some y right. Suppose y alpha, then there is an open neighborhood of y alpha, right, which is mapped homeomorphically onto an open set in X by F. Uh, so if you take that open neighborhood of y alpha, which is mapped homeomorphically by F with this V, then you will get an open neighborhood of y alpha, which is contained in V. And also that also will be mapped homeomorphically by V by F, right, and to an open set in X. I can verify. Now, so for each point in V, you can get such small open neighborhoods, right? So V you can write as union of some U alphas, right? Such that we have restricted over U alpha from U alpha to F of U alpha is a homeomorphism, right? And of course, Fu alpha will be an open subset of X, open in X, right? But then what you have Fb is going to be alpha F of U alpha, right? Because F of U alpha is open for every alpha, union of arbitrary open sets is open, so F of B becomes, it is. Next, we have another lemma, a covering projection is a covering projection is a local homeomorphism, and a local homomorphism is an open map, so hence a covering projection you can conclude that is an open map also. So proof, let P from X tilde to X be a covering projection, and let X tilde be a point in X. So we want to show that there is an open set containing X tilde, which is mapped homeomorphically onto an open set in X. So since P is a covering projection p x tilde x has an evenly it has an evenly covered this has evenly covered open neighborhood users, right? Then, by definition, if you use an open, evenly covered open neighborhood, then P inverse U is a disjoint union of open sets each marked homeomorphically this is a disjoint union of open sets each mapped homeomorphically onto U by P. Let so because this x p x tilde belongs to U, so P inverse U is going to contain x tilde, but x tilde P inverse U is disjoint union of open sets. So x tilde is going to belong to one of those open sets, right? Let let U tilde contains let U tilde is an open set containing x tilde such that P restricted over U tilde from U tilde to U is a homeomorphism. This is a homeomorphism. This completes the proof, right? So we have chosen arbitrarily x tilde in capital X tilde, and we have found out an open set U tilde in X tilde such that P restricted over U tilde such that P restricted over U tilde is a homeomorphism from U tilde to U, where U is open. This completes the proof. This completes the proof. So a local homeomorphism, so every covering projection is a local homeomorphism, but a local homeomorphism need not be morphism need not be a covering projection. Example for this, you can consider uh, P from this 3 to S1 uh, defined by P of t equal to exponential 2 pi I t. So this is basically restriction of exponential map over this open interval 0, 3. So since P is restriction of, so you can just observe that restriction of a local homeomorphism on an open set is a local homeomorphism. Since P is a restriction of a local homeomorphism, right? That exponential map is a covering projection, and hence it is a local homeomorphism. Is a restriction of a local homeomorphism onto on an open set 3. It is a local homeomorphism but it is not a covering projection, because if you consider 1 comma 0, right? So because so if you just let us just draw this 0, 1, 2, 3. This is 0.1, 0, right? So by definition, here 0 and 3 is not here. But this point and this point, they go to this point, right? Now, if you choose an open R, right? So we can claim that this point 1 comma 0 has no evenly covered uh, open neighborhood, because if you choose any open neighborhood, right, which will be an open R containing this 1 comma 0, right? So then it doesn't matter how small this open R containing 1 0 is. Its inverse image is going to contain an open interval containing this point 1, another open interval. If you choose this uh, open arc is small enough, then this another open interval containing this point, and you will have an open interval like this. and then another open interval like this, right? But you see, this is going to be mapped homeomorphically into this. This also is going to be mapped homeomorphically into this. But this open interval will be mapped to then see this open arc, right? Which does not contain 1 0, and this one is going to be mapped to this open arc, which does not contain 1 comma 0, right? So so this 1 comma 0 does not have any uh, evenly covered open neighborhood. So observe that 1 comma 0 does not have any evenly covered open neighborhood. So we have some corollary, a covering projection exhibits its space as a quotient space of its covering space, as a quotient space of its covering space. So suppose you have a covering projection from x tilde to x. Okay, then to prove that this is a quotient map, right? To prove that x is a quotient space of this x tilde by quotient map P, right? So P is a quotient map if and only if uh, P inverse U is open in x tilde even only if, so this is in this problem writing. So to prove that P is a quotient map, we prove that P inverse U is open in X tilde if and only if U is open in X. So of course, if U is open in X, then P inverse U is open in X tilde because P is a continuous map, right? Now, if P inverse U is open in X tilde, right, then we want to prove that U is open in X, right? So since uh, P is, because P is a covering projection and hence it is a local homomorphism, and hence it is an open map, because we have proved that every local homomorphism is an open map. So since P is an open map, P applied over P inverse U uh, is, which is equal to what? Which is equal to U is open in X, right? So here, because P is surjective, so P applied over P inverse U is going to be U itself. So if this is open, then because P applied over an open set is an open set, so P applied over this, which is U, will have to be open in X. So we stop here today.